Today's video is about another ATtiny feature, the analog comparator, or AC. I'll demonstrate on a Series 1 ATtiny, the 1614. We'll use the comparator to measure the frequency of a signal from a light source. A phototransistor will serve as a sensor that emits an analog voltage signal. What is an analog comparator? It's a device with two analog inputs called positive and negative, and one digital output called out. Out is high whenever the positive input is greater in volts than the negative input. This is the block diagram of the analog comparator on a Series 1 ATtiny like the 1614. Series 2 ATtinys are similar but have some differences. You can see that the software can select pins as analog inputs. The positive input is always a pin, but the negative input can come from an internal voltage reference or from a digital to analog converter or DAC. The latter choice allows software to change the negative input on the fly. We'll make use of this. The purpose of an analog comparator is to create a nice clean digital signal from the analog signals. This is a scope capture from an ATtiny. The digital signal out tells us when the positive analog input signal is greater than a threshold signal provided by a constant negative input signal. We can use this for analysis. For example, by counting the rising edges per second of the out signal, we can determine the frequency of a periodic positive input signal. This is what we'll do in this video. By the way, the negative input is not necessarily less than 0. The names are a little strange. On the ATtiny, both the negative and positive inputs are expected to be between 0 and VDD volts. The ATtiny comparator has some other features. Software can read the state of out and, often more useful, can command the comparator to generate interrupts on the rising edge, falling edge, or both edges of the output signal. We'll use this to count rising edges to obtain the frequency of the positive input. Here's a system diagram. Note the phototransistor on the left. It produces a voltage that depends on light intensity. This voltage is our positive analog input signal. I have an LED flashlight that blinks on and off quickly. The goal is to measure the frequency of this blinking and display it on the MAX 7219 7-segment LED display on the right. The MAX connects to the ATtiny via SPI. An oscilloscope shows us the signal from the phototransistor and the output from the ATtiny's comparator. The comparator negative input will come from an ATtiny DAC, but how do we know what voltage to set it to? We also run the signal from the phototransistor to a pin on which we can do an Arduino analog read. We read many samples of the input signal shown in yellow and find a max and min value for it. Then we set the comparator negative input to a value midway between the measured max and min. To see this better, let's look at the software. The first thing we see are some includes for libraries. This comparator library is part of MegaTiny Core, so you get it automatically when you install MegaTiny Core. I showed how to do that in my first video on ATtinys. The LED control library for the MAX 7219 7-segment LED display has to be installed using the Arduino library manager. And so here we define the pins that we're going to use for the 7-segment LED display and allocate an instance of that controller here. And then next I wrote a small function to display an unsigned decimal number on the LED display. So that just uses the setDigit method that's part of the LED control library and is pretty simple. And next we come to the interrupt handler for the interrupt coming from the analog comparator. And this is very simple. All it does is increment an 8-bit volatile counter. And then the main loop can read that counter to see if interrupts have occurred. And it's important that it's 8 bits wide because this is an 8-bit microcontroller, so loads and stores to 8-bit quantities are atomic. So there's no ambiguity if you read the counter in the middle of it being updated. Moving down to setup, we first initialize the LED display like this. Not much to say about that. And then we initialize the comparator. And notice this notation. I'm saying comparator 1. The 1614 has 3 comparators, so they're 0, 1, and 2. And I decided to be explicit about which one I'm using just because I can. If you leave off the 1 and just say comparator, I think it gives you the first one. But you can be explicit by using the number 0, 1, or 2. And then the first thing we do is we set up which pin is going to be the positive input. And so I'm choosing the first choice in 0, which corresponds to PA7. And you can see that in the datasheet, that correspondence. And then next I'm selecting the negative input to come from an internal DAC. And that means we can adjust the value of the negative input. And in order to use the DAC, we have to set a voltage reference. So I'm choosing to set it to 4.3, which implies that the maximum output from the DAC into the negative input can be 4.3 volts. And then I'm initializing the DAC setting to 127. That's kind of arbitrary at this point. And that would give a voltage of 127 divided by 256 times Vref, or 4.3 volts. So it's changing DAC ref that allows us to change the level of the negative input. And the hysteresis topic is interesting. I'm selecting to make the hysteresis large, and comparators usually should have hysteresis enabled. And that's because when the negative and the positive inputs are nearly equal, the comparator can become confused or oscillate about whether to be high or low. It's not a very stable state when the difference between the positive and the negative inputs is very, very small. So for the comparator value, you can choose large, small, medium, or disabled. But I think turning it on is almost always a good idea. And then finally, we're saying that we do want to enable the output pin, which for comparator 1 on the 1614 is PB3. And then after you do all of these initializations, you call comparator 1 init, and that sort of applies them. I can attach my interrupt handler and choose rising edge. I do that here. And then comparator1.start actually starts the comparator operating. Now let's move down to the main loop. And the key to this is this while loop here. And what that does is it runs for interval milliseconds, so 1 second. And during that 1 second, it does two things. It counts interrupts, and it also samples the positive input pin and keeps track of the minimum and maximum values that it sees. And it's going to use that in the next interval to set the value of the negative input so that we position it in such a way that we're likely to see the interrupts. And there's a little bit of complexity in how the interrupts are counted because I'm using that 8-bit volatile counter, but I need to count more than 256 interrupts. And so I do that by getting a kind of a quick snapshot of the current 8-bit interrupt count, and then I see if it's changed and by how much. And so I'll increment edge count by the amount that it's changed, taking care of the fact that the 8-bit counter might have wrapped around. So it might have, gone from 255 to 7 or something like that. So I have to get that number of interrupts correct when it does it. And then here's where we keep track of the minimum and maximum values. And so after the interval ends, it's time to compute and display. But the first thing we do is take our maximum and minimum values and we convert them to millivolts and calculate a mean, because that's what we want to set the negative input to for the next interval. But that mean can't be greater than 4.3 volts. So I check that here. And then I set the output value of the DAC for the negative input like this. And there's no direct API for a dynamic change in the comparator library from ATtiny Core. So I'm writing that register directly, and I see no reason why that doesn't work. And then after all of that, I just display the current edge count. And then the next time the loop runs, it'll reset edge count to 0, set us up for the while loop to go for the next 1 second, and continue the process. So it might take a couple of seconds to have a correct value displayed. And it also requires that the positive input signal be periodic and stable over a couple of seconds. But this is how the software works, so let's see it in action. The system's running. Up at the top, we can see the ATtiny 1614, and over here is the programmer that I used to program the ATtiny. Down here, we have the Max 7219 display that's going to show the edges detected per second. And over here is our photo transistor. And on the right, you can see an oscilloscope display. And the yellow trace is the output from the photo transistor, so the input to the analog comparator. And the magenta trace is the output from the analog comparator. I'm going to use this flashlight that I built as the stimulus for the phototransistor, so I can turn this on and off. And this is an interesting flashlight. I'll leave a link to the schematic that implements it below, but it blinks at about 10 kilohertz. So now I'm going to put the flashlight right next to the phototransistor and turn the flashlight on. And we should see a signal on the oscilloscope, and I'll have to fix its triggering, it looks like. Okay. And so now on the upper right of the oscilloscope display, you can see that it's measuring about 10.45 kilohertz. And the ATtiny is measuring something similar. So it's working pretty well. And I can use the cursor to show the threshold. That will be where the rising edge of the yellow signal intersects the rising edge of the output, the magenta signal. So that's Y2, about 1.66 volts. So that's the threshold that our dynamic threshold computing logic computed, that we saw that in the code before. So now if I move the flashlight around, I can make this curve move, and the threshold will have to be recalculated. And we can see if the count remains accurate. So if I move it back like this, then it looks like the counts are still accurate on both the oscilloscope and the ATtiny. But now I'll show you the new threshold. So it'll be this point here where those curves intersect. So now Y2 is about 2.72. So I can make it more challenging and get the flashlight kind of completely out of your display, but make a weaker signal. And we can see that the counts are still accurate from the ATtiny. And let's adjust the trigger on the oscilloscope. And the oscilloscope's measuring about 10.4 something kilohertz still, so they're still consistent. And now the threshold is up to around here. And so that's Y2 is about a 4 volt threshold. So the threshold's changing as I move the flashlight around. So I can move it close again, get our nice signal, adjust the trigger on the oscilloscope, and now the threshold is back down to about here, about 1 point, I can't read it, 1.7 volts or something like that. So the system's working pretty well. And if I turn the flashlight off, the count will drop back down to 0. I'll end this video here. We've seen an introduction to the analog comparator on the ATtiny. Thanks for watching.